All right, so lecture 23, we're talking about combinational logic circuits. In the technology news of the day, I saw this wonderful article on Tech Review about a delightful solution to the robotics problem. People have used Arduino to program robots, but if you want to have a really serious computing situation, you don't just have a little Arduino thing, you need to have a real computer there. So how do you compress a computer down to be big enough to be able to, small enough to be able to be on a localized robot? And people have tried, and some Google engineers created this wonderful Android brain, which is using all of the Android circuitry to do the most of the simple computing stuff. Using the Android sensors, like the GPS and the camera and some other things, the sound and microphone and all that stuff, locally. And here's the best part, because it's a GPS phone, because it's a normal phone, you've got the cloud behind it. So any heavy lifting in terms of image processing or something can be done by the cloud. Really very clever, and you may see a whole new slew of folks. I totally bless, even though I'm an Apple guy, I totally bless the Android space as a kind of do-it-yourself thing for that space. I love that. And I wish Apple would be more open to that kind of thing for Apple devices. Okay, so in review, we talked about state elements. And specifically, we saw that there were state elements and combinational logic elements. The state elements we looked at last time, and a lot of that was about timing, right? We saw they were used to build memories. D flip-flops were the core of any register. The clock was what drove those things. If you had a lot of them in a row and you had a lot of these delays, like a T adder and a T shifter and a T other stuff, you might actually pipeline those. We'll see that a little bit more in this class. That's not the last time you're going to see pipelining. And at the end, we talked about finite state machines as being a great and really efficient way of encoding a way to have kind of a brain. You know, this is, I've taken a coin mode. Now I've taken 5 cents, but I haven't taken a full yet dollar, so I don't release the soda. That's the kind of idea of a finite state machine. We saw the particular example of counting 3 ones in a row, and not 4. If it gets to 4, it resets. It has to have another 3. So it sees 3 and resets it. We saw that example. So if we have a truth table, you're going to see a connection between finite state machines and combinational logic and truth tables at the end. In fact, your last slide, you'll see this wonderful picture that shows the 3. So truth tables, you can see, as being important when we're talking about combinational logic. Today is about combinational logic, so none of the issues of that state, none of the issues of the timing really come in here. We're not going to talk about timing anymore in this lecture. Let's just talk about just pure logic. This is just the fun part. This is the part that's totally digital. I'm going to make a box called F, 4 inputs, A, B, C, and D, has 1 output, Y. And this is kind of the generic output, right? This is the generic output. Whatever that particular F has is what I have here. So as an example, an AND, if F were a 4-input AND gate, what would the right column look like? Give me some love. People who don't usually talk in the back here, give me some love. Yeah. All zeros, and then the F1111 would be a 1. Correct. How about if F were a 4-input OR gate? Give me some. Someone normally doesn't talk. All 1s except for 0 up top. Exactly. And you can imagine other interesting 4-input gates. So I'm going to ask you a question. How many different Fs can I have? I go to Radio Shack and I buy the AND is a particular sequence of these guys. So I go to Radio Shack and they give me the and that's 1 F. That's F sub 1. And I go by the OR, and that's F sub 2. That's another pattern. How many different Fs could Radio Shack sell that are 4-input, 1-output boxes? 2 to the... I count 2 to the 4. Is that right? Is and and OR just one of the 16s? What do you guys think? 2 to the 2 to the 4. 2 to the 16. Does that sound right? 65,000? 64K? Yeah. Take a look at this F. And everyone, when you're reading a smiley for the first time, they told you, turn your head 90 degrees and look at the smiley, right? Everyone look at this F series and turn to the left. That is a 16-bit value, right? And each particular one of those is a signature for a particular F. And so that maybe is 2 to the 16. Isn't that cool? Kind of neat way to think about this. So here's one of the most important ones we're going to see. This guy is called an XOR. And actually, I think this is an XNOR. Isn't that right? This is an XOR. Oh, no, yeah, this is an XOR. This is an XOR which says one or the other, but not both. And this is really important. And one of the reasons it's important is this really cool property, which is if I look at only A, I think I did this before, how does A relate to Y? If I set A to 0, how does B relate to Y? I mean, I'll do it again. What's it do? Pass through, right? Buffer, identity, okay? What if A is 1? How does B relate to Y? It's an inverter. You know what we call XOR? A conditional inverter. Because when I don't want it to invert, it just passes it through. When I want it to invert, I set A to 1 and it flips it. Isn't that kind of cool? So it's like thinking of that inverter triangle guy as having a third input here that says, do you invert or not? And if you invert it, a little circle comes at the end, meaning it's an inverter. Otherwise, it passes it right through. Isn't that kind of neat? Right? B and Y are the same, or B and Y are different, depending on what A is. Okay? So those are two important things. Now, we've got the case that we're going to see that we're going to need an adder. At some point, we have to have circuitry to implement add, register, register, register. So we're going to need an adder. And let's start small. A 1-bit adder is nice, but let's think about a 2-bit adder. So here's a 2-bit adder, and here's the truth table. So you're saying, Dan, all I know how to do to build circuitry is to do it by a truth table means. Okay, here's a truth table. Guess what? This, A to B, is a 4-input box. And the lowest order output bit might be one of those Radio Shack boxes. And the second order guy might be another Radio Shack box. Notice they're all different, right? Look, these are 3 different rows. This column is different. C2 column is different from C1, which is different from C0. So you can imagine going to Radio Shack and buying 3 of those particular Fs that implement the C2, C0, and C1 column, and walking away done, and considering that a successful 2-bit adder, right? You can do that pretty easily. So one question you ask is how many rows, and that's pretty easy. If I have 4 input bits, then I have to be able to handle every possible condition of that, so therefore I have 16 rows in that truth table, right? Not too bad. 3 columns because I have 3 outputs, but the 16 rows is the important part of that. So now we're going to generalize this. Is MIPS all about 2-bit numbers? No. MIPS is about 32-bit numbers. Okay. So now, here's my 32-bit. Oh, by the way, you can verify this works, right? This is the sum of A and B. So when A is 1 and B is 3, C is 4, right? If A is 3 and B is 1, it's 4 here. 3 is 6, right? So this all makes sense. If you look at that, you verify this was correct. So now, we're going to take our only tool we have, which is to look at the truth table model to start building these things and go back. And we're going to say to ourselves, okay, how many rows in this guy? Yeah. Oh, yeah, ask a question. Sure. Questions are great. Go. Can you go back another slide? Bing. Good thing I don't have too many animations, otherwise it'd be really annoying. Sorry? Or the one before. Okay. How about the front one? I keep going. No. I will. You can't stop me. I don't want to stop you, Jerry. You can't stop me, Kramer. You can't stop me. Stop this one? The solution to this was what? I don't think I asked a question. This was just a particular generic F with 4 inputs, and this is the generic solution. I never have to show another slide about this. The particular signature is whatever particular Radio Shack box I buy. If it's all zeros and a 1, then it's an AND box. If it's a 0 and all 1s, it's an OR box. It could be ignore A and just be a 3-input AND box, in which case it would ignore A and it would be the same value ignoring, the top 8 would be the same as the bottom 8. There wasn't a question here. It was just more of a general talk. Okay, so the open question is still, how many rows on this truth table to do our generic 2 input, each input has 32 bits wide on my line, adder, unsigned adder. Rohan, go. 2 to the 64. That sounds right. For each of the columns of C. I mean, that's them are rows, and now I have to have a different 2 to the 64 signature for each of those columns. So 2 to the 64 is the answer. Who feels like writing down those 2 to the 64 different entries? Who thinks that's the right way to go about thinking about adders? No hands. That's good. No hands is the right answer. Good job. So let me now show you another really important example, and then maybe we'll talk about how to do a generic adder by the end. In fact, I know we will. Okay. Here is a 3-input majority circuit. And you may have never seen this table before, but this is a really useful table. And essentially, you know that San Francisco is coming up with a vote for their mayor, and they're having this special way they do election preferential voting. You should read about it. It's kind of neat. politics right across the bay. You're supposed to vote and rank order your candidates, and this is complicated. They're using the word algorithm and news. I love it. And they use an algorithm. I'm like, yay, algorithms. They talk. You know, I love influencing the public with computer science ideas. That's good stuff. So this is a majority circuit in which you basically are having three of you. Who's ever played this game where you want to choose among three of you, and you go like rock, ones, twice, three, shoot. You either put a 1 or a 0, and then whoever happens to be the odd person out gets chosen to go downstairs to get the pizza you ordered or something. So look at this. This is the majority, right? If all of them are zeros, it's 0. If the 1's an outlier, then the 0 is the majority and 0 wins. If 2 out of the 3 are 1s, then a 1 wins. It's kind of cool, right? It's a majority circuit. You can imagine that. And that's very useful in cases. We're going to see why this is useful. But that's another truth table. That's one of the 2 to the 8 possible 3 input, 1 output boxes you might buy at Radio Shack. But it's important one we're going to see a little later. These are the classic 3. These are the 3 you can build anything out of. Okay? I even told you that you can build and, or, and not out of a NAND. Who did that? Who decided to go back and play with that? 1, 2... Okay, 3, good. Get some points to these guys. That was good. Good for you. Good for you. More of you should do this kind of things that I throw out there as fun puzzles. So here's an and, or, and a not. Some of you saw how to build those out of a NAND gate. This is the fundamental building blocks. And you've all seen this probably before, but you may not have seen the particular schematics. When I was going through this stuff, I would always confuse and or. I would never remember whether it's a square edge or a round edge. So I decided to have a mnemonic, which was this. And once I had this mnemonic, I never forgot it the rest of my life. How about that? So that's a little gift from me and me only, so you don't forget this. Another cool thing is that and is Dan, rotate left. You know, remember the one that you rotate left and the D goes around with the thing and the bit that falls off the end and runs around the back? Okay, so that's and is Dan, rotate left. Okay, these are also useful. Thank you so much. As supplementary, let me grab that from you. Perfect. Okay. As I do this, excellent. Okay. XOR, NAND, and NOR, which are XOR I've shown you before, but that's the drawing for XOR. It's an OR with the little guy in the front. Okay, it's kind of neat. And you're not supposed to draw the line through. See that? It's very cleverly drawn. You don't draw this line through that. It's supposed to kind of buffer in front of it, which is nice. Here's NAND and here's NOR. Remember, the little circle at the end means you just invert the output. And if you look, this is actually exactly an AND with everything just inverted, switched. So that's why we call it a NAND, not and not or. Okay, questions about so far? So far, nothing brain-busting, right? Okay. This is a 3. Sometimes when you extend 2 input gates to n inputs, it's seamless. Like an n input and is, look, it's only 1 if all of them. All right, that's easy. But some are a little bit more complicated. So here's an n input XOR, and here's how we think of it. An XOR, by the way, if you look back at the XOR here, XOR is really a 1 only when the number of 1s there is odd. Notice the number of 1s here is 0. Here it's 2, so I don't count it. It's really counting whether the number of 1s is an odd number. So, but if I didn't tell you that, then you wouldn't necessarily know what an XOR was, right? Because XOR I usually say is one or the other, but not both. But what does it mean for XOR of 3 inputs? And here, in general, the way you extend XOR to be n inputs is you only output a 1 for XOR if and only if the number of 1s that you saw is an odd number, same as the 2-input guy. So that's how that extends to n inputs. See, 1, 1, and 1 for the 1 guy, and then only when it's 3 do you get a 1 again. Otherwise, it's a 0. Okay? So that's an n-input XOR, and now you can extend it to a 6-input XOR, and now it just makes sense. You do that. Another way to think about this, by the way, this is another cool thing. An XOR, another word for XOR in combinatorial game theory is called the nim sum. Another way to think about it is you add this up, and you don't carry. And if you add something up and don't carry, what's the lowest bit? Well, that's a 1 only if the number of 1s is a 1. So this is 3, right? What's 3 in binary? 1, 1. What's the lowest bit? 1. Therefore, XOR is 1. So another way to think of XOR is you just do a normal add of all those 1s, and then look at the 1s bit at the sum of that non-carrying sum. And you say, if that 1s bit is a 0, therefore it's an even number. Even number of 1s you saw before. Otherwise, it's an odd number, and therefore it's a 1. Okay, that's XOR for multiple inputs. So this is how you might implement a truth table. So here is the gates connection from the truth table. We're going to see in this class how you can go from the truth table to gates, and that's one of the things we're learning now. Here's the majority circuit. And let's verify that this actually works. Let's just walk this through. Let's see. Okay, it's a 1 if let's do the first one. B and C, then it's a 1. Okay, B and C, or A and C, and there's A and C, or A and B, and that's there. But there's also what happens. Don't you need another one? Don't you need A and B and C? Don't you need that? Well, it turns out you don't need that term because you've covered all the cases already. Anytime A and B and C are true, then it has to be true that one of A and B or B and C or A and C. Actually, all of them. All these guys will fire. But you don't need any more than this, which is really cool. So here's another way to think about this. This is the truth table that came out of the finite state machine that we built on Friday to count the 3 ones. Remember there was a 1 here, and that was the only time that your output was when you were in the second state. You were counting S2. S2 told you that you had seen 2 ones before, and only when you saw another 1 do you go back and output a 1. This is the output as a function of these guys. Look at this. It only outputs a 1 when PS sub 1, the higher bit, is a 1. PS sub 0, the lower bit, is a 0. So you've put a little inverter in there, and watch what happens. Input is a 1, and basically I want to see 1, 0 of 1, and the 1, 0 of 1, this inverter becomes 1, 1, 1. Therefore, it's only true when I see 1, 1, 1. And AND means they all have to be true. So by inverting the bits that are not the case, I have this really pretty pattern where I basically have, give me a bit pattern. 101. Well, then I say 1. Whenever you said, I put an inverter there, and I put all that in an AND gate, and now I get something that only goes high when the exact bit pattern is present on those input bits. 1, 0, 1, the 1 becomes a 1, 1, 1, and therefore only that guy is only going to trigger high when all of those are true. Therefore, only that signature is going to be the case. Isn't that nice? So if you want to write a code, so I've taught you now, if you ever want to have a circuit that goes high when an exact bit pattern is true, just flip all the guys that are zeros and pass with these little mini inverter guys, pass it into an AND gate that'll only register high when that exact bit pattern is the case. Isn't that kind of neat? Okay. So, by the way, you can also push this little inverter guy up into the input, and that's kind of the standard way people write this. So you see this little bubble guy at the input, it means only invert this one signal. You see the output, you mean invert everybody, right? Invert the output of the whole thing. So let me introduce you to a historical figure in computing engineering, George Boole. There's a nice picture from Wikipedia, 19th century mathematician. He developed a language for talking in this binary way, and we called it Boolean algebra. It was an algebraic system, a delightful, fully complete, robust. He was a mathematician, so it's a complete mathematical system. Essentially, if your numbers were only 0 and 1. The primitive functions that he came up with back then, a long time ago, were and or not, which connected one-to-one with what we've used as our building blocks. So we've actually leveraged all of his work and when we were first building computers. It's really very cool. How we talk about it now is we want to talk about this in algebraic terms. We're going to see a connection between these gates and expressions in which, in the future, in the following, this slide and from now on, when you see a plus, you think into your mind or. When you see times, you see and. And when you see a variable with a bar on top, you think not. That's it. That's how you make the connection. So let's look at this guy. What is this guy in now an expression? Can you give it to me? A times B plus B times C plus A times C. There it is. And now we just compress them with the dots as you do in multiplication, and that is the way that you would send the information of this picture. Otherwise, you're taking a picture on your cell phone and you're selling it to your friend. Now you can text. Hey, see, I've told you how you can text circuitry now. Isn't that great? That's good stuff. You can tweet it. You can now tweet this. Go. Who wants to tweet this? Hey, I learned about this thing. Y equals AB. And you're basically tweeting this circuit, but good luck in trying to tweet a picture in 144 characters. Okay. Questions so far? Yes, good hand. Go. Is there an order of precedence? Very interesting. There isn't. We're going to assume that as addition is commutative, so is ors, and as multiplication is commutative, so is our and. So no worries about the order of that, okay? This is beautiful, which is nice, okay? That said, we're going to allow you to have parens. If there is some time when you have something times something plus something, that actually matters how you do it, and therefore will give you parens, just like you have in algebra. It really is kind of cool. So here is this truth table. I've got this code, I've got this, and this is how I'd write it. Now, one of the things you might notice is my variables have multiple characters here. And if you didn't have the explicit dots, it would be kind of weird. Like, do you mean the variable p and then the variable s sub 1, or do you mean the variable ps sub 1? Does that make sense? So whenever you have this kind of case, you almost always leave them with dots between, so there's no confusion of, where's the variable p? I don't have it. Well, it's not the variable p, it's ps is the variable, right? So that's how you write it, okay? We'll leave it like that. Kind of cool. So now, this is where it gets interesting and fun. I have this original circuit. I can do the same manipulation I did in algebraic terms on my Boolean algebra. So I can take a circuit and simplifying it by moving to this Boolean algebra term and then going back. You're going to see this again when you, this wonderful idea that you can transform to another way to represent it. You do some manipulation and you transform back. Okay? You're going to try to say, oh, I'm in Photoshop. I want to take this picture. I want to convolve it, which is like smear it with this filter. I don't know what the output is going to look like. What if you went to the frequency domain? You can then multiply them, which is very easy. Then you go back to the spatial domain, and there's your convolution. Like, what? I used a lot of words you didn't know, but there's this cool idea that you can go to one world, do some stuff that might be easier in that world, and then you come back to the original world. Isn't that awesome? So we're going to see that here. You'll see that a lot of times in EE. It's really powerful when you see it here in circuitry terms. So I have this circuit. I want to simplify it. I don't know how to actually rewire it by that, but I do know how to manipulate symbols. So, and I can even have a computer do that symbol manipulation for me. You know, the Mathematica does a lot of this kind of stuff for you. So let's start. Here's my original circuit. I write it like this. Y equals A times B or plus A, right? Or A. Or C. And you say, is that as simple as you can get it? Because why do we care about having things simple in the first place? Why aren't we done with this? Isn't this fine? Why would we want to simplify? Go. Each of those things is a transistor, or a couple of them. I want to reduce the amount of wasted transistors I have. It takes more power, it takes more size. The larger my die, the lower my yield in terms of printing a fab plant, so I make more money. So it's all about money, people, at the end of the day. Okay. So, A plus B or C, that's sum, or plus A, that's sum or C, all right? So now, let's work slowly. I can even, as I have a Mac, do this. Okay, so let's do this now. Here we go. This is hopefully going to help people on the webcast also, because you get much less resolution on that. Okay, so let's try it. What do we got? Well, this is all in addition. I can take the parens away, right? It's all in addition. You don't need that. That simplifies it. A plus B plus A plus C. Now, look at this. I can take the A out. I can kind of undistribute, using the distributive power, the A out of that expression, and I get B or 1. You're going to see that B or 1, okay, when are you true? You're true when all the time, which is the 1, or when B is the case. Well, you're still true with the 1, because the B is a special case of that. So B plus 1 is 1. A times 1 is A, just like math. Isn't it wonderful? A times 1 is A, and you get A plus C. Look what I did. Compare the difference. I feel so good. Look at this. Becomes one block. Isn't that cool? And that's really, really cool. So thank you, George Boole, for all the hard work. He did all the heavy lifting. I'm just riding on the shoulders of giants, and he's a giant, so it's awesome stuff. This is also, this purple block is also important to you know. The purple block says the following. It says, if I need to find out if two circuits are the same and they're really complex, that's hard to do. But what if I simplified them both to the simplest terms? A lot easier to do. Okay? And it might be the case that even in the simplest terms, they're a little bit the same but a little bit different. But it's easy to compare the two things that are simpler than the complex guys, right? Okay. So this is the slide of the laws of Boolean algebra. How many of these don't make sense already? This is the beauty of connecting this with mathematics. Ready? X plus 1, well, X plus 0 is X. That we knew already. you didn't probably know, you also know that x times 1 is x. You probably didn't know that x times 0, oh, actually you knew this one. These two you knew. You didn't know this one, right? This is one that's new to Boolean algebra. Look at this, right? X plus 1 equals 1 means that x better be 1. Not the case. X could be 1 or 0. It's still 1 in this Boolean sense. We just saw that before in that example before, right? X plus not x is 1. So if I'm like, let's see, I'll let you come in my house if you're either human or not human. Guess what? You're coming in my house, okay? How about you can only eat pizza if you're human and you're not human. That's impossible. So that's a 0, right? Okay? Now, this one always gets people, so I actually did this. These are my notes, and people, I would probably guess you would pronounce it incorrectly, so?
Idempotent.
So now, that's the official dictionary.com. Let's do it a couple times. If you download this slide, you get it for free also. Ready?
Idempotent.
It's not idempotent, right? It's idempotent, right?
Idempotent.
Idempotent, okay? Pretty cool stuff. And this is not, this doesn't make any sense for normal number algebra, but it makes sense in Boolean sense. 1 and 1. Variable x and x. And you just talk about x. It doesn't complicate it anymore to add it. How about, oh, you can come in if you're a human or if you're a human. Come in if you're a human. It's the same kind of thing, right? Commutativity is the same as normal math. Associative is the same as normal math. Distribution is the same as normal math, okay? This one is a little bit, basically uses another term in here. So this is really x plus y times x plus z. That gives you 4 terms. Remember the FOIL method, first output, or this? If you boil it down, the x's cancel. X times x becomes x. So this is a little bit of a couple of things together. There's 2 uniting theorems, and this may be the most important thing of all. This is the coolest one. This is called De Morgan's law. Again, standing on the shoulders of giants, De Morgan is a giant of the field. The De Morgan's law tells you if you've got a not and you've got an or, how you can make an and. It's so cool. Here's how you make an and. If you have a not and or, how to make an and. It's really cool. So here's how I think of De Morgan's law. And by the way, if you have a not and an or, how you can make an and. If you have a not and an and, you can make an or, back and forth. It's a duality. It's this beautiful duality that you're going to see. Okay? I haven't talked about duality yet, but I have this great idea. In the world, there's usually 2 things, right? There's good and evil. There's 0 and 1. There is and or, right? There is time and frequency. There are lots of things you're going to see. And in this De Morgan's law, it lets you convert from one side to the other. It's this beautiful thing. So you can not from one side to the other. You can also not your way from an and to an or. And that's this cool, powerful De Morgan thing. So here's how I think of it. This bar that you draw across which says, that bar, by the way, this expression on the left, the bottom left, I'm talking about for those in the webcast, this guy here, as I point to the screen with the clicker, that doesn't help people on the web. So this bottom expression, okay, this is a NOR gate, right? It's saying x, that's a NAND gate, That's a NAND gate. That says x and y, not the whole thing. That's a NAND gate. And I think about the following. What if I take the not and distribute it over to all terms? The x, the y, and the operator. If I negate, is this cool? See, if I negate the x, you get not x. Negate the y, you get not y. If I negate the and, you get an or. Isn't that cool? So that's a way to think about this connection between and or and the beautiful duality thing. So that's called De Morgan's law, powerful stuff. So we're going to ask you to memorize those things. We're going to ask you to give, well, you have a cheat sheet on your exam. So we're going to ask you at the very least to have it on your cheat sheet as I ask you to simplify an expression to a simpler terms. So here's this guy. A times B or A or C. You'd write down, as you would kind of a proof in geometry, that I can pull the A out, and that's distribution. That's also the identity law that lets me pull the A out of that guy. B plus 1 is the law of 1, simplifies this guy, and identity is the A times 1 is A. So you'd write these things on the right, and you would simplify it as you see on the left. It's pretty cool. It's pretty powerful that you can get to this stage to do that. And I think I'm almost at the clickers time, so I should get this guy ready. We went a little faster than I thought we would for this lecture. So any questions before I go to the clicker is up? One more thing before I go to clicker. Okay. So this slide talks about canonical forms. You say, what do you mean canonical forms? There's an idea of being able to take a truth table and make an expression. And then later I can try to bubble it down to the most canonical form. So we start with the sum of products. Canonical means like the one way you represent it that's shared among everybody. So here I have these 4 terms. 4 guys that made my y. And remember, just like before, here's the signature. And whenever I want to write down what this is, I put a not in front of the guys that were zeros. So this is A, B, C, A, N, B, and C. And this is A, N, B, and not C, like we saw before. You put a not in front of all the guys that are zeros. And if I said, what's that truth table in an expression in Boolean algebra, you basically say, it's this case, or it's that case, or it's that case, or it's this case. Each of those cases is an and of those 3 terms, with maybe a not applied here and there. And that's what you get. You normally are not going to get the simplest form doing this. Okay? You're normally not going to get that, in very rare cases. But that's when you're Boolean algebra massaging. And that's where you get your hands dirty. That's where you dip your hands into the juice of the Boolean algebra simplifying expression. You start massaging. You start the juice. You're now juiced up with the hands. And now you start massaging those expressions until you get the simplest form. Right? You're trying to shake out all the dead leaves and make this purest form. So here is that example. My hands dripping with Boolean algebra expressibility. And now I can say, what can I do? Oh, look, there is not a b that's constant for those 2 terms. There's 2 different arguments, so I pulled that out. Basically, the first step usually is distribution. You pull out the common terms to get these guys. And now, here's the law of complementarity, which is going to say C or not C is a 1. You got to be, if you're a human or not human, you can come in. You're definitely coming in then. And so that puts a 1. Identity then simplifies it, and there's your simplifying form. Isn't that cool? Kind of cool stuff. I love this stuff. I think this is really, really fun and important because you saw the importance of being able to do this. And by the way, you can get computers to do this infinitely faster than you can. This, a big, huge term, do this, and that's all kind of things that Mathematica is built on. Yes, question, Chris.
With De Morgan's law, can x and y, can they also be other Boolean algebra expressions?
Yes. No. Each of the question was in De Morgan's law, can x and y be Boolean expressions? The answer is 100% yes. X and y can be itself a single bit, or it can be the convolution of an expression. You can think of that expression feeding down to one line, and that one line you can then use De Morgan's law. And so the answer is 100% yes to that. Yep. Okay. Questions on the canonical forms, part 2? I think we're down at the clicker time. Yes, in the back. Hey, go. They are the same. Equivalent means the same. Oh, well, talk about efficiency. What do you know the answer? If they're the same in terms of they're the same in terms of, let's see. Oh. They're not the same. This guy, I need a 4-input OR gate. The top guy needs I need 4 3-input AND gates. Oh, these 2, the bottom guys. Oh, the bottoms are the same. Yeah, the bottom guy is just this bubbles moving to the bubbles. But the top guy to the bottom, if I decided to make this into a circuitry, I'd have 4 AND gates, I'd have scattered inverters, and I'd have a 4-input OR. That's certainly much simpler. The bottom 2 are 100% the same. It's just ways that we draw them. I'm talking about the top to the bottom. But I didn't show you the picture for the top. Okay. All right. So this is one that you may need more time than normal to answer. So the first one is this equivalent? Here's this expression. Is it the same as B? So go write this up. Next one. N input gates can be thought of as cascaded 2-input gates. Okay, i.e., A, operation B, C, operation D, operation E could be thought of and distributed like that as the 2-input gates, okay? Where the operator is either AND or XOR or NAND. The last question is, you can use NORs with clever wiring to simulate AND or and not. I told you can do it with NAND, but I didn't tell you can do it with a NOR. So the question is, can you or can you not do it with NOR, okay? And let me just think about one. You certainly need some time to think about one as you work on it. And I'm going to get this thing launched here with my clicker guy. This is my new base. Thank you for getting that for me. Okay. Create ideas, new architecture, yes. Start session, yes. And start and Did I show slides? Is that the answer? I might show the answer. Okay. Shh. This first voting time is a solo time, and then we talk to our neighbors. So let's try to keep it quiet for the first one and look straight ahead. Can I have a TA volunteer to count people? How many people we have here? Just somebody get up and try to see. Yeah, just to count today. See how we're up to. No, we're not. That'll just give us a sense of clicker percentage per person here, and that'll be good. So. That's right. It's true, but people are very shy to do that kind of thing. You guys all, who needs more time? 1, 2, okay, give you a couple more minutes. I'll make sure everybody gets it right. And then you'll talk to your neighbors, but stay quiet if you could until everybody's voted in. By the way, if you raised your hand for the person who spoke earlier with the handouts are right in the front. So make sure to pick those up. Don't forget that when you leave. Okay? All right? Maybe that's a good time. All right? Talk to your neighbors. Go. Okay, when you're ready, vote in again with your team. Hold hands, vote together, same vote. Let's see how you did. As a meta point, I hope you found these clicker questions overall useful to kind of keep the class engaging. That's the reason we do them. We just try to kind of break the time up and to get you feedback. Right now, I can ask a question that would be on the midterm. And I can just see whether you get that right or not. So that's a useful thing as well. Okay, we're almost at the number we had before. So there's that one. And let's see what it looks like, how it differs from before. Okay, bink, 3, 2, 1, bink. So a heavy CD, and before that, it's also, sorry, heavy DE before that. So let's take a look at the answers here. So the first one, if you work out A or B, and not A or B, well, you do the FOIL method, and you break it up into this, and A and not A is 0, and B can pull out of here, which is A or not A, and there's a B, which is B and B is B. A or not A is true, so that's 1. B and 1 is B. B or B is B. So I get true. Yay. That's the first one. The second one is on the next slide. The third one is, can you do this to make a NOR and De Morgan's law is the guy that really gives it to you. If it weren't for De Morgan's law, then you wouldn't necessarily have that connection, but because of De Morgan's law, you do. It's kind of cool. So here is the confirmation of this is the correct 3-input, guys. It's false. So the answer actually is, I think it was D. This is what the correct 3-input guy is, and this blue guy is what you get if you take and cascade. So blue is the cascading guy. So AND matches up. If you cascade 2-input ANDs, you get it same as a 3-input AND. So does OR. XOR, oh, look, also matches up. But NAND kills you. So NAND is the guy that you can't cascade, actually. It's good for you to know. If you want to cascade 2 to 3 and you want to make a 3, you can't do it with NAND. You can do it with XOR, but you cannot do it with NAND. It makes sense for XOR because XOR is like an addition, so you can always cascade an addition in terms of adding pieces of it. And the difference is NAND is only true in the 3-input case and only false with all 3 are 1s. But the problem is if you NAND like a 1 and a 1, you get a 0. And then that 0 and another 0 gives you a 0. I think that's right. Oh, 0 and 0 gives a 1. Wait, that's interesting. What did I do wrong? 1 and 1 is a 0. And 0 and a 0. NAND, oh, 0 NAND 0 is 1. Doesn't that match up? What am I doing wrong? Zero and 0 is 1, but why shouldn't that be a 1 then? Why doesn't that match up? I might have done this wrong. I thought I tested this and I didn't. Let's try it. 1, 0. Well, let's try the 1, 0. 1 NAND 0 is a 1, and then that is a 0, but it should be a 1. At least this case is wrong. I might not have this blue guy right, but at least this case is wrong, right? 1 NAND 0 is here. 1 NAND 0 is a 1, and then 1 NAND 1 is 0, but it should be a 1. Sorry? No, the black and the red are what it should be correct for a 3-input guy, right? And this, it ends up that 1, 0 cascaded to 1 is a 0. So that line is exactly wrong. Not all of them are right. Yeah. Oh, is that what it is? I'm sorry. So this blue guy is I take the right 2 first and cascade it with X. Because look, here's Y, Z. So I am cascading Y and Z, then adding an X. So thank you. So I'm right. Then the point is that right? So the right 2 bits. So let's this way. 1, 0. Yeah, because all these 3 are all 1s, and 1 NAND 1 is 0. So that's exactly right. Yeah, thank you. It's the right 2. It's still correct. I just was cascading wrong. Thank you. Okay, before I jump out, you still have 5 minutes, actually. I'm early. I want to show you this. Go to slide, my hidden slide I didn't show. Yay. So the next project is going to have a performance component, and we are going to celebrate the winners. So the next project is about making the fastest piece of code ever. And so I also want to do a check. I did this at the end of project 1. This is where you get, and I will now display for the world how many hours you put in. And this is good feedback for us, right? This is good feedback for us. By the way, the number you should say is, well, let's think about it. You have how many contact hours a week with us? Let's think. 3 lecture, 1 discussion, 2 lab, right? That's 6. A 4-unit class is at 12 units. So you're supposed to spend no more than 6 hours outside of class every week for any 4-unit class that has 6 hours of contact hours. 6 times 2, actually it was a 2-week project, not a 4-week, right? 2-week project, 12. I'm looking for 12, and I'm getting a B-ish 12. So I'm feeling very happy this project was fair. Yes, question? Did I do it wrong? Oh, man. Okay. So the person who made my slides totally messed up. They're not very smart. That was me. But the key is, go and pretend that C, let's edit C. That was ridiculous. I don't know who's making my slides at 4 a.m., I don't know, which is when I did my slides. So don't do your slides at 4 a.m. is the summary, and let's fix that. Now, the clicking is still live, so just go and fix your thing now. Just revote, and it'll be fine. Don't worry. Okay. Feel free. Thank you for that. Okay. I'm going to have to fire the person making my slides here. Okay. So, project 2, we're still getting a sweet spot of B, which is right. 12 should be the right answer. And you, in theory, should be spending 6 hours no longer per week on any one of your 4-unit classes that has 6 hours of contact hours. If it's more, then you are being overworked. Or you can think about it, you're getting more for your dollar. That's another way to think about it. Okay. Thank you for that feedback, folks. I'll let you go a little early. And let me jump to the conclusion as you walk out. Here's the picture. Don't stand in front of my slides. That's kind of cool that you can now go from anywhere to anywhere, but I haven't yet shown you how to go from truth table to gates. Okay? So that's pretty cool. I'll leave this up as I'm closing out.